In part C, we're asked to find the radius of convergence of the Taylor series for f about x equals 0. Now there's two ways that we could go about doing this. One way is we could use the derivative, the nth derivative that was given us above, recalling that the nth term of a Taylor polynomial will be the nth derivative, especially a Taylor polynomial for f about x equals 0 will be the nth derivative of f at 0, then times x to the nth over n factorial. So we could use the formula that we had above. So we could take the formula that we were given above, and that's really our nth derivative of f at 0. And we would still have to divide that by n factorial and multiply that by x to the nth. So then a sub n is equal to negative 1 to the n plus 1 times n plus 1 factorial over 5n times n minus 1 squared, then an n factorial in the denominator, and x to the n. So that would be my n plus nth term. Now we could simplify this a bit because n plus 1 factorial over n factorial is really just n plus 1. And so we end up with negative 1, n to the 1 plus n, negative 1 to the n plus 1 times n plus 1 over 5n times n minus 1 squared, all times x to the n power. So to find the radius of convergence, we need to find the radius of convergence, but we don't need to check the endpoints. So we want the limit as n goes to infinity. And recall, because we're working with absolute values, we can neglect the negative 1 to the n plus 1. And we would just have, again, we're working with our n plus first term, so it's in the numerator n plus 1 factorial, or n plus 2 factorial. Sorry, we're not working with the factorial, it's just n plus 2 times x to the n plus 1 over 5 to the n plus 1 times n plus 1 minus 1, which is just going to give us n squared. And instead of dividing by the nth term, we're going to multiply by the reciprocal of the nth term. So that would give us 5 to the n minus 1 squared in the numerator. And it would be n plus 1 times x to the n in the denominator, absolute value. Alright, so we can simplify this. And first we have our n plus 2 over n plus 1. And the limit of that as n goes to infinity is just 1. And then we have n minus 1 squared over n squared. And the same principle, as n goes to infinity, that's going to be 1. Then we have 5 to the n over 5 to the n plus 1. And that's going to turn out to be just 1/5. And finally, in absolute values, we have x to the n plus 1 over x. And that's going to turn out to just be the absolute value of x. Sorry, that was absolute value of x to the n plus 1 over x to the n. And that simplifies to just be absolute value of x. The ratio test, limit as n goes to infinity, yields us absolute value of x over 5. And that will converge when that is less, and the series will converge when that is less than 1. But here we're asked for the radius of convergence, and the radius of convergence is just that 5. With the radius of convergence, we don't have to test the endpoints, and that's it. So I'm only going to show that one way. We could have done this using what we did above, but we would have had to come up with a general term, but that general term would not have differed from what we ended up with down here, and we still would have had to do the same ratio test. Now in the remaining seconds on this video, when you're doing an interval of convergence, which you have to do to find a radius of convergence, there are two ways. One, if it is a geometric series, you're looking for absolute value of r is less than 1. Otherwise, if it's not a geometric series, you have to do the ratio test, the limit as n goes to infinity of the absolute value of the a sub n plus 1 over a sub n terms, and where that's less than 1, the series will converge.